Deep beneath the border of France and Switzerland, a 27-kilometer machine drives particles together at nearly the speed of light. Collision after collision, it recreates tiny flashes of the early universe, then searches the wreckage for clues about what reality is actually made of. Most of the time, the answers follow the rulebook perfectly, but not always. Scientists have found strange signals hiding inside the data. A particle that seems to break apart the wrong way. Matter behaving differently from its mirror twin. Antimatter trapped, released, and watched to see whether it falls like everything else. For more than 50 years, physics has trusted one powerful theory to explain the universe. Did scientists just find a crack in reality? Let's find out. Picture a circle so large it crosses an international border, buried deep beneath ordinary ground. Above it, the world looks calm. Cars pass through quiet villages. Farms stretch across the countryside. The Alps rise in the distance, still and ancient, as if they have nothing to do with the secret machinery humming below. But roughly 100 feet beneath the surface, under France and Switzerland, a tunnel curves through the darkness in a perfect ring. And inside that ring, particles race faster than anything humans have ever learned to control. This is the Large Hadron Collider, the biggest science machine ever built. Its underground ring stretches for 27 kilometers, looping from Switzerland into France and back again. If you tried to walk one full lap, it would take most of the day. Workers use bicycles and service vehicles to move through parts of the tunnel, because this is not just a machine. It is an underground world built for one purpose: to smash the smallest known pieces of matter together and read the universe from the wreckage. The particles sent around this ring are called protons. A proton is one of the tiny pieces inside an atom. And an atom is already so small that millions of them could sit side by side across the dot at the end of a sentence. So the machine is not throwing rocks together, or even grains of sand. It is throwing pieces of the invisible world together, pieces so small that no eye could ever see them directly, yet so important that nearly everything around you is built from them. Inside the tunnel, these protons move at nearly the speed of light. A beam of protons can circle the entire 27-kilometer ring thousands of times every second. To guide something moving that fast, thousands of powerful magnets are placed around the tunnel like the ribs of a giant metal creature. These magnets bend the beams around the circle and keep them focused, narrow, and controlled. But the magnets can only do their job if they are made superconducting, meaning electricity flows through them with almost no resistance, like water moving through a perfectly smooth pipe. To make this possible, engineers cool them to temperatures colder than outer space, close to absolute zero, the lowest temperature nature allows. So deep underground, this place becomes a world of strange opposites. It is colder than the darkness between stars, yet it creates flashes hotter and more violent than almost anything around us today. Then comes the collision. Two beams of protons are sent around the ring in opposite directions, one clockwise, the other counterclockwise. For most of the journey, they are kept apart, like two rivers moving through separate channels. But at certain points inside the machine, the beams are aimed directly into each other. Head on, proton against proton, matter against matter, moving almost as fast as light can travel. The crash is unbelievably small, but the energy packed into it is enormous. For a fraction of a second, in a space smaller than an atom, the collision becomes a tiny furnace. The familiar pieces of matter break apart, and new particles burst outward like sparks from a firework. Most of them vanish almost instantly. Some live for less than a trillionth of a second, born, traveling a microscopic distance, and disappearing before light could cross a grain of dust. That is why scientists do not watch particles the way we watch birds in the sky. There is no tiny camera that photographs a proton exploding. Instead, collision points are surrounded by detectors, enormous machines that work like three-dimensional cameras for the invisible. These detectors are built in layers, like the rings of a tree or the walls of a cathedral wrapped around a single point. When particles fly outward from a crash, they pass through those layers and leave tiny signals behind. Each signal is like a footprint in snow. One footprint tells you almost nothing. But if you follow a trail, you can learn where something came from, where it went, and how fast it was moving. The detectors collect those traces, reconstruct paths, measure energy, and work backward to understand what happened in the collision. The particle itself may be gone, but its shadow remains. The scale of this is almost impossible to hold in your head. Collisions happen millions of times every second. The machine produces more information than any human could ever read, more raw data than ordinary computers could store if they tried to keep everything. So lightning-fast systems decide in a tiny fraction of a second which collisions are worth saving and which can be discarded forever. Most events are ordinary. Most follow the rules. But hidden among them may be one rare crash that points to something new. This is why the Large Hadron Collider was built, not simply to make particles crash, but to ask matter what secrets it has been keeping. Every collision is like opening a book for a single instant before the pages burn away. Scientists have to read the ashes. They look for patterns, for missing energy, for particles that decay in unusual ways, for tiny differences between what the universe does and what the laws of physics say it should do. And this is where the story becomes unsettling. For decades, physicists have used one incredibly successful theory to describe the particles and forces of the microscopic world. It is called the Standard Model. It predicts how particles should behave with astonishing precision. Again and again, experiments have tested it, and again it has survived. It is like a map that has guided scientists through every known valley, mountain, and ocean of the subatomic world. But no map is the territory itself. And scientists already know this map is incomplete. It does not explain dark matter, the invisible substance that seems to outweigh ordinary matter across the cosmos. It does not include gravity in the same way it includes the other forces. And it does not fully explain why the universe is made mostly of matter instead of being empty light. So the goal is not only to confirm the rulebook. The deeper goal is to find the first place where it fails. That failure may not arrive as a giant explosion or a brand new particle appearing clearly on a screen. It may arrive as a whisper, a particle falling apart at a slightly wrong angle, matter behaving just a little differently from antimatter. A rare event happening just often enough to make scientists wonder whether something unseen is pulling from behind the curtain. That is what makes this machine so powerful. It is not just a machine of force. It is a machine of patience. It repeats the same impossible act billions upon billions of times, waiting for nature to make one tiny mistake, or to reveal that what looked like a mistake is actually a deeper law. In the darkness under the border, every collision is a question. Most answers say the rules still hold. But every so often, the data seems to lean another way. And lately, some of those answers have not been as simple as scientists expected. To understand why the strange signals matter so much, you have to step away from the machine for a moment and look at the universe like a film running backward. Today, the cosmos looks wide and cold. Galaxies drift through darkness like islands in an endless ocean. Stars burn inside those galaxies. Planets circle those stars. On one small world, oceans move, clouds gather, and living things are built from atoms that seem stable and familiar. But this peaceful picture is only the last frame of a much older story. Rewind the film far enough, and the universe becomes stranger with every second. Go backward past the birth of Earth, past the first stars, past the first atoms, and the whole universe begins to squeeze together. Space grows hotter, denser, brighter. The distances between things shrink until the familiar architecture of reality disappears. There are no planets, no rocks, no water, no air. Even atoms cannot hold their shape. Everything that now seems solid melts into something more ancient. Less than a second after the Big Bang, the universe was not filled with objects. It was filled with energy and restless particles. A glowing ocean where the ingredients of matter had not yet settled into the forms we know today. Protons and neutrons had not yet become the stable building blocks inside atoms. Their smaller ingredients, called quarks, moved through a hot, dense state alongside the particles that carry the forces between them. Scientists call this state quark-gluon plasma. The name sounds technical, but the image is simple. Imagine the universe before it became a finished book. The letters were there, the ink was there, but the words had not yet formed. Quarks are some of the letters from which matter is written. Gluons are like the binding threads that usually hold those letters together inside protons and neutrons. In the world around us today, quarks are locked tightly together. You never find a single quark sitting alone. They are confined, sealed inside larger particles like stones built into a wall. But in the first moments of the universe, the heat was so extreme that the wall had not yet hardened. The quarks and gluons moved more freely, like sparks flying loose before cooling into metal. That ancient state vanished as the universe expanded and cooled. But scientists can bring back a tiny echo of it. Not the whole beginning, not the Big Bang itself, but a microscopic droplet of the kind of matter that filled the early cosmos. To do this, they sometimes collide heavy atomic nuclei instead of single protons. When those heavier particles smash together at nearly the speed of light, the energy can become intense enough to briefly melt their inner structure. For the smallest fraction of time, quarks and gluons behave as if they have been freed from their usual prison. The droplet is unimaginably small, and it disappears almost instantly. Yet in that flash, scientists can study a piece of the universe as it may have existed when time itself was young. What they found was surprising. This early universe matter does not behave like a thin gas, as many might expect. It flows more like a liquid, but not like water, honey, or oil. It appears to be one of the most perfect liquids ever observed, moving with extremely little internal friction. If ordinary liquids are like rivers dragging along stones and mud, this plasma is closer to a glassy stream, sliding almost without resistance. It is matter in one of its most extreme forms, yet it moves with a strange smoothness. That discovery matters because the early universe was not just a fireball. It was a system with behavior, structure, and rules. The way that first matter flowed helped shape everything that came after. As the universe cooled, quarks became locked into protons and neutrons. Those later formed atoms. Atoms gathered into gas. Gas collapsed into stars. Stars forged heavier elements. And those elements eventually became planets, oceans, bones, and blood. The path from the quark-gluon plasma to a living world is impossibly long. But it begins with the behavior of matter in those first moments. This is why the collider is sometimes described as a time machine. It does not send people into the past. it does something more precise. It recreates conditions from the past in a controlled place and lets scientists watch how matter responds. A telescope looks backward by catching ancient light from distant stars. The collider looks backward by rebuilding ancient heat in a tunnel beneath the Earth. But the deeper purpose is not only to understand what the early universe looked like. It is to understand how the universe changed. How did a hot, featureless ocean become a cosmos full of structure? How did the simplest ingredients arrange themselves into the great architecture we see today? Somewhere in that transformation, the rules of physics shape the future. The same rules that decide how a particle decays in a collision also help decide whether stars could form, whether atoms could survive, and whether matter could outlast antimatter. That is where the story begins to tighten. If scientists can recreate tiny pieces of the early universe, they can test whether the laws we use today are enough to explain the journey from the first fire to the world around us. And so far, the answer is uncomfortable. The laws explain a staggering amount. They describe particles with almost impossible accuracy. They predicted discoveries before machines were powerful enough to find them. They are strong enough to feel like bedrock. But bedrock can still hide cracks. The early universe left behind questions that the known rules do not fully answer. Why did matter survive when matter and antimatter should have destroyed each other? What is the invisible dark matter holding galaxies together? Why do particles have the masses they do? Are there forces that shape the young cosmos but are too faint for us to detect today? Each collision is part of that investigation. Some recreate ancient matter. Others produce rare particles that decay in delicate ways. Others let scientists compare matter with antimatter, like two reflections in a mirror. The machine moves between the smallest scale and the largest mystery, because in physics, those are often the same thing. To understand the ocean, sometimes you have to study a single drop. Every mystery needs a rulebook before it can become a mystery. If you walk into a room and see a glass fall from a table, you do not panic. Gravity pulls things down. That is the rule. If you throw a stone into a lake, ripples spread outward. That is the rule. The universe may look wild and endless, but underneath the motion of stars, atoms, light, and matter, there are patterns that hold with astonishing precision. For the world of the very small, the most powerful pattern humans have ever found is called the Standard Model. The name sounds almost boring, like a manual left in a drawer. But behind that plain name is one of the greatest achievements in the history of science. The Standard Model is the rulebook for the smallest known building blocks of reality. It tells scientists what kinds of particles exist, how they interact, which forces guide them, and what should happen when they collide, decay, or transform. Think of it like a periodic table, but deeper. The periodic table describes atoms, the ingredients of chemistry. The Standard Model goes underneath atoms and describes the ingredients of the ingredients. It tells us about quarks, the tiny pieces locked inside protons and neutrons. It tells us about electrons, the lightweight particles that help build atoms. It tells us about neutrinos, ghost-like particles that pass through matter almost as if the universe were transparent. It tells us about photons, the particles of light, and about other force-carrying particles that act like invisible messengers between pieces of matter. In this rulebook, the universe is not made from an endless collection of random objects. It is made from a surprisingly small cast of characters. A few families of particles, a few forces, a few deep rules. From that small hidden alphabet, nature writes everything we see. Hydrogen clouds, burning stars, iron mountains, ocean waves, human hands. The entire visible world rises from combinations of particles so tiny that no ordinary picture can truly hold them. What makes the Standard Model so powerful is not just that it organizes what scientists already know. It has predicted things before anyone had seen them. Again and again, the mathematics pointed toward a particle that should exist. And years later, experiments found it. It is like discovering that a missing stone must fit somewhere in an ancient arch, then digging through the ruins and finding the exact stone waiting in the dust. The W and Z bosons were predicted, then discovered. The top quark was predicted, then found. And most famously, the Higgs boson was hunted for decades before it was finally revealed in 2012. That discovery was not just another particle added to a chart. It confirmed the existence of a hidden field spread through all of space, a field that helps give elementary particles their mass. The universe had followed the rulebook so closely that even its most delicate predictions became real. That is why physicists trust the Standard Model so deeply. It is not a guess. It is a theory tested across decades, across machines, across countries, across billions of measurements. Scientists have tried to break it in every way they know how. They have smashed particles together, measured decays, trapped antimatter, studied rare processes, and pushed the math into places where even a tiny error would show. Most of the time, the Standard Model does not flinch. But here's the strange part. Scientists also know it cannot be the final answer. That sounds impossible at first. How can the most successful theory ever built also be incomplete? But science often works that way. A map can be accurate and still not show the whole world. Newton's laws were powerful enough to send rockets toward the moon, but they were not the deepest description of gravity. Einstein revealed a larger picture. In the same way, the Standard Model may be a brilliant map of one layer of reality, while a deeper continent remains hidden beyond its edges. The missing pieces are enormous. The Standard Model does not explain gravity. It describes three of nature's fundamental forces with incredible success. But gravity stands outside the structure like a mountain range drawn on a separate map. Gravity shapes planets, galaxies, black holes, and the expansion of the universe. But it does not fit neatly into the Standard Model's machinery. Then, there is dark matter. Astronomers can see its influence in the way galaxies spin and cluster, but no known particle in the Standard Model can fully explain what it is. The visible world, everything made of atoms, stars, dust, planets, and people, appears to be only a small fraction of the total matter in the cosmos. Most of the universe's matter is invisible, and the Standard Model does not identify it. There is also the mystery of matter and antimatter. The laws we know suggest the early universe should have produced both in nearly equal amounts. Matter and antimatter should have destroyed each other, leaving almost nothing behind. Yet matter survived. The stars survived. We survived. The Standard Model contains some differences between matter and antimatter, but not nearly enough to explain why the universe did not erase itself at the very beginning. So physicists live with a strange tension. They hold a rulebook that works with breathtaking accuracy, but the universe keeps pointing beyond it. It is like standing in a cathedral whose walls are perfectly built, whose arches hold, whose windows glow, and still noticing that some doors are sealed from the other side. Something exists behind them. The building itself tells you that, but you do not yet know how to enter. This is the real reason the Large Hadron Collider matters. It was not built only to confirm what scientists already believe. It was built to push the Standard Model until it reveals its limits. To find the first crack in the stone, to discover whether there are new particles, new forces, or hidden connections that have escaped every experiment so far. But the crack may not look dramatic. It may not arrive as a brand new particle suddenly appearing in the data with a clear label attached. Nature is rarely that generous. New physics can hide indirectly, like a heavy object behind a curtain, never seen directly, but still pulling the fabric out of shape. If an unknown particle is too heavy for the collider to produce, it might still influence a rare decay. It might tug on a particle for a fraction of a second, just enough to change the final pattern. That is why scientists study particle decays so carefully. A decay is what happens when an unstable particle falls apart into lighter ones. Some decays are common and well understood. Others are incredibly rare, happening once in a million tries or less. Those rare decays are precious because they are quiet places. In a noisy room, a whisper disappears. But in a silent room, even the smallest sound becomes important. Rare decays are those silent rooms. If something unknown is interfering, the disturbance becomes visible. The standard model predicts not only which decays should happen, but how often, what particles should appear, and even the angles at which those particles should fly away. That is an almost unbelievable level of detail, like predicting not only that a glass will shatter when it hits the floor, but the exact pattern of the shards. So when a decay does not match the prediction, scientists pay attention. They do not immediately shout discovery. They do not claim the universe is broken. They check the detector, the software, the calculations. They ask whether ordinary physics could be wearing a strange disguise. But if the same unusual pattern appears again and again, in more data, in different analyses, and especially in different detectors, the tension grows. This is where the mystery begins to take shape. Inside the wreckage of collisions, scientists have been watching certain particles containing beauty quirks. These particles are heavy, unstable, and short-lived. They appear for a moment, then fall apart. Most of the time, they behave exactly as expected. But in some rare decays, especially those involving muons, the details have not lined up as cleanly as the standard model says they should. The difference is subtle. It is not a monster stepping into the room. It is a shadow moving where no shadow should be. A slight lean in the data, a strange angle, a pattern that keeps returning instead of fading away. And because the standard model has been right so many times before, even a small disagreement becomes significant. The stronger the rulebook, the more important every exception becomes. The crashes inside the collider happen too quickly to see. So scientists do something clever. They do not try to watch a particle live. They study how it dies. Some particles are stable enough to build the world around us. Electrons can last for an enormous stretch of time. Protons, as far as experiments can tell, are also remarkably stable. But many particles created in collisions are different. They are heavy, restless, and temporary. They appear in the fire of a collision, carry too much energy to remain as they are, and almost instantly transform into lighter particles. Scientists call this transformation decay. The word sounds like something slow, like wood rotting in a forest. But particle decay is not slow at all. Some particles live for less than a trillionth of a second. They exist for a distance smaller than a human cell, sometimes smaller than an atom, and then they are gone. There is no way to catch them with ordinary senses. By the time a detector notices anything, the original particle has already vanished. But it leaves evidence behind. Imagine hearing a glass shatter in another room. You do not see the glass fall, and you do not see the moment it breaks. But when you walk in, the pattern of shards on the floor tells a story. Some pieces are large, some are tiny, some flew far, some stayed near the table. From the wreckage, you can reconstruct what happened. Particle physics works in a similar way. The original particle is gone, but the pieces it became are still moving outward, carrying information about the event that created them. This is why decays are so important. They are not random explosions. They follow rules. A particle can only fall apart in certain ways, and each possible path has a probability. Some paths happen often, others are almost impossibly rare. The Standard Model predicts these paths with astonishing precision. What a particle is allowed to become, how often it should choose one route over another, and in many cases, what shape the final spray of particles should take. So every decay is a test. If a particle falls apart exactly as expected, the rulebook holds. If it falls apart in a slightly different way, scientists begin asking why. Maybe the measurement is imperfect. Maybe the calculation is incomplete. Maybe the detector misread the trail. But there is another possibility, the one that keeps physicists awake at night. Maybe something unknown briefly entered the process, touched it, and disappeared before it could be seen. This is where rare decays become powerful. A common decay is like a crowded city street, noise everywhere, motion everywhere, and one strange footstep is hard to notice. But a rare decay is like a quiet mountain lake at dawn. The surface is still. Drop one pebble into it, and every ripple becomes visible. If new physics exists beyond the Standard Model, rare decays are some of the best places to look for its fingerprints. One of the experiments built for exactly this kind of search is called LHCB. While other detectors are enormous general-purpose machines designed to study many kinds of collisions, LHCB is more specialized. It focuses on particles containing beauty quarks, also called bottom quarks. These particles are heavy, unstable, and especially useful for studying tiny differences between matter and antimatter, as well as rare processes where hidden forces might leave a trace. Think of LHCB as a detective standing beside a busy road, not watching every car, but looking for one rare vehicle with a broken headlight that passes only once in a million times. Among the most interesting cases are decays that scientists have nicknamed penguin decays. The name sounds almost ridiculous, and its origin is famously playful. Physicists often draw particle interactions as diagrams with lines showing what transforms into what. One particular type of diagram involved a loop and several outgoing lines, and someone joked that it looked a little like a penguin. The name stuck. So now, in serious scientific meetings, researchers can discuss penguin decays while exploring some of the deepest mysteries in physics. But behind the strange nickname is a very serious idea. In these decays, a beauty particle transforms through a process that is rare and delicate. It may produce particles such as kaons, pions, and muons. Muons are heavier cousins of electrons, similar in many ways, but about 200 times more massive. They appear often in some of the most intriguing anomalies in modern particle physics, which makes their role in these decays especially interesting. The Standard Model predicts how these decays should unfold. Not only how often they should happen, but also the detailed geometry of the particles that emerge. When the original particle breaks apart, the final particles fly away in different directions, like sparks from a firework. Those directions are not meaningless. They carry the memory of the forces involved in the decay. Scientists measure these directions using carefully designed quantities called angular observables. The phrase sounds complicated, but the meaning is visual. Imagine trying to understand an explosion by studying the shape of the debris field. Did the pieces fly evenly in all directions? Did some prefer one side? Did the pattern twist slightly away from what you expected? In particle physics, the angles can reveal whether the known forces are acting alone or whether something unseen is helping shape the outcome. For years, LHCB has studied a rare decay involving a beauty meson turning into a kaon, a pion, and two muons. The decay is extremely uncommon, which makes it valuable. If an unknown particle or force is influencing it, even faintly, the effect may show up as a small shift in the angles. The hidden particle does not need to appear directly. It can act like a hand behind a curtain, moving the fabric without ever stepping into view. And this is where the mystery deepens. In some measurements, the angles did not sit exactly where the standard model predicted. The difference was not enormous. It was not a dramatic explosion of new physics. It was a lean, a stubborn drift, a pattern that seemed to sit slightly off to one side. The kind of difference that would be easy to dismiss if it appeared once, but harder to ignore when it keeps returning. This particular tension has been discussed for years. Early hints appeared more than a decade ago. At first, scientists treated them with caution, as they should. Particle physics is full of statistical mirages, patterns that look meaningful until more data arrives. But the anomaly did not vanish immediately. New analyses continued to study it. More collisions were collected. The measurements became more precise. And the same question remained hanging in the air. Was the particle really falling apart the wrong way? To answer that, scientists have to compare the data with the standard model prediction. But that comparison is not simple. The decays involve quarks bound together by the strong force, one of the most difficult forces to calculate in detail. Some ordinary standard model processes, especially those involving charm quarks, may blur the prediction. If those effects are larger than expected, they could imitate the appearance of new physics. This is the frustrating beauty of the problem. The anomaly might be a doorway, or it might be a shadow cast by known physics that scientists have not yet calculated perfectly. The data is whispering, but the room is not silent enough to hear every word clearly. Still, the reason physicists care so much is that rare decays have a history of revealing deeper truths. Sometimes the universe shows the footprint before it shows the creature. A new particle may be too heavy for the collider to create directly, but it can still influence what lighter particles do. It is like discovering a large planet not by seeing it, but by watching a distant star wobble under its gravity. The unseen object announces itself through the motion of something visible. That is what scientists are looking for in these penguin decays. A wobble, a tilt, a tiny departure from expectation that cannot be explained away. If the anomaly survives future data and sharper calculations, it could mean the standard model is missing something. Perhaps a new force that treats muons differently from electrons. Perhaps a new particle acting as a bridge between families of matter that are usually kept separate. Perhaps something stranger than any current theory imagines. Any of these would be enormous. Not because they would answer every question at once, but because they would prove that the known map has an edge. For now, no one can honestly say that has happened. The evidence is intriguing, but not final. It has not reached the level required for a confirmed discovery, and physicists are careful because they have been fooled before. The strange thing about this mystery is that it does not begin with something huge. It begins with a number, a tiny number, a stubborn number, a number that sits just far enough from the prediction to make scientists uncomfortable, but not far enough to let them celebrate. Imagine an archer shooting arrows at a target from miles away. The standard model tells scientists exactly where each arrow should land. Now imagine that after thousands of shots, the arrows keep landing slightly to one side. Not scattered randomly, but leaning in the same direction again and again. At first you blame the wind, then the bow, then the ground under the archer's feet. But if every check comes back clean, the question becomes harder to avoid. What is pushing the arrows? That is the feeling behind this anomaly. The measured angle in certain rare decays has appeared displaced from what the standard model expects. The shift is not a final discovery, but it is not meaningless either. It has lasted long enough to become one of the most watched tensions in modern particle physics. Scientists do not treat it as proof. They treat it as a clue. And a clue can be powerful when it points toward a locked door. To judge a clue like this, scientists use statistics. They ask how likely it is that a strange result could appear purely by chance. Flip a coin 10 times and getting 7 heads will not shock anyone. That is ordinary randomness. But if you flip it 100 times and nearly every result is heads, luck stops feeling like a good explanation. Physicists measure that suspicion with a term called sigma. Sigma tells them how far a result has wandered from ordinary expectation. 1 sigma is weak. 2 sigma is interesting. 3 sigma makes people look closer. 4 sigma becomes difficult to ignore. 5 sigma is the golden threshold, the level usually required before scientists officially call something a discovery. That threshold exists because when you search enough places, chance will sometimes build a pattern that looks meaningful. Physicists know this because they have been fooled before. Around 2015, data showed a strange bump involving pairs of photons. It appeared in 2 major detectors, which made it exciting. Theories spread quickly. Papers appeared. For a moment, it looked as if a new particle might be standing just beyond the standard model. Then more data arrived, and the bump disappeared. It had been a ghost made from ordinary events clustering in an unusual way. Not a mistake, not foolishness, just a reminder that nature can create mirages. That is why scientists are careful with the rare decay anomaly. It may be real, but it may also fade. The fact that a result is strange does not make it true. The fact that it is exciting does not make it final. Still, this mystery refuses to feel ordinary because it connects to a wider pattern involving beauty particles, rare decays, and muons. The muon keeps appearing near some of the most interesting tensions in modern physics. In the standard model, electrons and muons should be almost the same apart from their different masses. They are like 2 versions of the same instrument playing the same melody in different keys. But what if the muon hears a note the electron does not? If nature treats muons differently in a way the rulebook does not allow, that would be a major crack in the standard model. It could mean a hidden force is touching one family of particles more strongly than another. It could mean a new particle is acting like a secret messenger between parts of matter that were thought to be separate, like a hidden hallway connecting 2 sealed wings of the same building. The unknown particle might be too heavy for the collider to create directly, but it could still influence rare decays indirectly. It would be like an unseen hand briefly reaching into a machine, nudging one gear, and vanishing before anyone can photograph it. The machine still runs, but one dial is slightly off. That dial is the decay pattern. Yet there is also a more ordinary possibility. The standard model may still be right, and the apparent mismatch may come from calculations that are extremely difficult to perform. Beauty particle decays involve quarks bound by the strong force, one of the hardest parts of physics to calculate. One troublesome effect involves charm quarks. which can briefly influence the decay in ways that are hard to account for cleanly. If that influence is larger than expected, it might imitate the signal of new physics. The mystery could be a shadow cast by known particles, not a doorway to unknown ones. So the situation balances on a knife's edge. On one side, the anomaly may be a crack in the standard model. On the other, it may be a difficult corner of the standard model itself. Either answer matters. If it is new physics, it could open a path toward forces and particles no one has ever seen. If it is known physics misunderstood, scientists will still sharpen their understanding of how matter behaves at its deepest level. That is why the next round of data matters so much. More collisions mean more rare decays. More rare decays mean clearer patterns. A true signal should grow stronger as the picture sharpens, like a coastline emerging from fog. A false signal should fade, like a reflection disappearing when the water settles. This is the slow drama of real discovery. It is not always a single moment where someone shouts that everything has changed. More often, it is a long climb through uncertainty. A measurement appears. It survives. It is challenged. It is repeated. Then, it either strengthens into truth or dissolves into chance. For now, the standard model has not fallen. It still stands massive and elegant, like a stone bridge carrying physics across half a century. But beneath that bridge, in the river of data, something keeps disturbing the surface. The ripples are small. The source is hidden, and every new collision sends another wave across the water. The mystery at CERN is not only about one strange decay. It is about what that decay might be pointing toward. If the rare beauty particle anomaly survives future tests, it would mean something unseen is reaching into the deepest machinery of matter. Not loudly, not like a new planet appearing in the sky. More like a hidden current under the ocean, changing the direction of a ship before anyone can see the water moving. One possibility is a new force of nature. We already know a few forces that shape reality. Gravity pulls planets, stars, and people. Electromagnetism gives us light, electricity, and magnetism. The strong force binds quarks inside protons and neutrons. The weak force helps particles transform and decay. But there may be another force, quieter than the others, one that has stayed hidden because it only whispers in rare events. If such a force exists, it could explain why some particles seem to behave slightly differently from expectation. It might touch muons more strongly than electrons, or influence beauty quark decays in a way the standard model does not allow. That would be revolutionary. It would mean the universe has another layer of architecture, another invisible beam inside the building carrying weight we never knew was there. Another possibility is a new kind of particle acting as a bridge. The standard model separates particles into families, each with its own role. Quarks build protons and neutrons. Leptons include electrons, muons, and neutrinos. In the known rulebook, these families interact in carefully limited ways. But some theories imagine a hidden particle that could connect them more directly, like a secret passage between two wings of a palace that everyone thought were sealed apart. If that hidden bridge exists, it could appear first not as a visible particle, but as a slight distortion in a rare decay. The decay would still happen. The final particles would still fly outward. But the angles, rates, or patterns might shift, as if the process had taken a route through a hidden corridor. But the story is bigger than this one anomaly. The same machine has already changed how humanity understands reality. It confirmed the Higgs boson, showing that an invisible field fills all of space and helps give particles their mass. That discovery explained why the universe can build solid things instead of remaining a blur of massless light. Every stone, every tree, every human body depends on that hidden field interacting with the particles inside matter. The collider has also helped scientists study antimatter, the mirror substance that should have existed in equal partnership with matter at the birth of the universe. Researchers have created antihydrogen, trapped it with magnetic fields, and compared it with ordinary hydrogen. They have tested whether antimatter behaves like matter under gravity. And the answer so far is beautifully simple. When released, antihydrogen falls downward. That result may sound ordinary, but in science, ordinary can be profound. For decades, some wondered whether antimatter might fall upward, whether gravity might treat the mirror world differently. If it did, it could have rewritten our understanding of the cosmos. Instead, antimatter fell like everything else. One wild possibility was crossed off the map, and the central mystery remained. If antimatter behaves so much like matter, why did matter survive while antimatter nearly vanished? This is the rhythm of the collider. It opens doors, and sometimes it closes them. Both are valuable. A closed door tells scientists where not to look. An open door reveals a longer corridor. The search is not a straight road from question to answer. It is more like exploring a vast underground city with only a lantern. Each measurement lights one archway, one chamber, one staircase, while the darkness beyond remains enormous. The public often imagines discovery as a single dramatic moment. A screen flashes, a scientist gasps. A new truth appears fully formed. Real discovery is usually slower and more demanding. It is years of calibration, repetition, doubt, and argument. It is teams checking whether a signal is real, whether a detector is biased, whether the mathematics is complete, whether another experiment sees the same thing. Science advances not by believing the most exciting answer, but by making every answer survive. That discipline is why the strange signal matters even before it becomes a discovery. It shows exactly where the known theory is under pressure. The standard model remains astonishingly successful, but it cannot explain everything. It is a cathedral with missing rooms, a map with blank oceans at the edges. Dark matter is still unknown. The imbalance between matter and antimatter is still unexplained. Gravity still stands outside the particle rulebook. Somewhere, a deeper theory must exist. The anomaly may be the first loose thread, or it may not. That uncertainty is not a weakness in the story. It is the story. The universe is not required to give answers on our schedule. It does not reveal itself just because a machine is powerful or a theory is beautiful. It gives clues in fragments, a decay angle, a missing particle, a symmetry that cracks slightly, a measurement that refuses to settle. So beneath France and Switzerland, the collider keeps running. Protons circle the underground ring. Magnets colder than space guide them through darkness. Detectors wait like enormous eyes around the collision points. And with every crash, scientists ask the same quiet question again. Do the rules still hold? Most of the time, the answer is yes. But sometimes, hidden in the wreckage, the universe answers differently. Not loudly, not clearly, just enough to make the surface of the known world ripple. And if those ripples grow, if the strange signal survives sharper measurements and deeper tests, then this mystery may become something far greater than an anomaly. It may become the first clear sign that the universe has been carrying a secret chapter all along. A chapter written beneath matter, beneath light, beneath everything we thought was final. And the collider beneath the border may be where we finally begin to read it. Deep beneath the border of France and Switzerland, a 27-kilometer machine drives particles together at nearly the speed of light. Collision after collision, it recreates tiny flashes